In this video, we are going to prove this limit. If theta is measured in radians, then the limit of sin theta divided by theta is 1 as theta tends to 0. Do you remember that this is where we ended our last calculus video? And besides this limit, we are going to prove another limit which involves the cosine function, which will follow from this one. So let's see how the proof goes. The proof starts with this diagram. In this diagram, we have our usual x-axis and y-axis, and we also see a quarter of the unit circle centered at the origin, because we do not see the entire unit circle because this is what we need. But why? Well, let us first put theta in the standard position, so that the initial ray of theta is the positive x-axis and the final ray lies in the first quadrant, and that is why we are only considering this part of the unit circle which lies in the first quadrant. But again, why? Why should theta be like this? Well, because we want to know the limit of sin theta divided by theta as theta is approaching 0. So there is no point in considering a very big theta, because after all theta is approaching 0. So it's reasonable to consider only theta that is this much. However, another question arises. Because we want to know about the full limit, so theta approaches 0 from the right side as well as from the left side. When it approaches 0 from the right side, it is positive, which is what we see here, because this theta corresponds to an anti-clockwise rotation. But what about when it approaches 0 from the left side? Should we not consider a negative theta for that? Yes, we should. But luckily, for that we don't have to draw another diagram or do anything extra. Whatever we do and find about the positive theta case, that itself will somehow say something about the negative theta case automatically. So we will see that afterwards. Let us first concentrate on this. Alright, so now the terminal ray of this angle theta intersects the unit circle at the point P. You can also see that we have drawn a perpendicular from P on the x-axis whose foot is Q. But additionally, we have also extended the line OP, which intersects this perpendicular line at the point T. What is this perpendicular line? It is a line perpendicular to the x-axis and which passes through the point A. A is the point where the unit circle intersects the x-axis, so its coordinates are 1, 0. And there is one more thing. We have also joined A and P by a straight line segment. Alright. Now, what are these lengths? Let's see. Because theta is being measured in radians, and because it has been put in the standard position, and this is the unit circle, we know what the coordinates of P are: cos theta, sin theta. As such, OQ is cos theta and PQ is sin theta. Okay, and because P lies in the first quadrant, both cos theta and sin theta are positive, and that is why they are not just coordinates but they are lengths of these sides as well. Something else also you can note. The length of OP is 1 because OP is one of the radii of this unit circle. Additionally, OA is also 1. But what is this? Why is this tan theta, AT? Well, you can note that we have two right-angled triangles here in this diagram. One of them is OQP, where Q is the right angle, and the other one is this large OAT, that is also a right angled triangle. So two angles are right angles, they are equal. These triangles have a common angle also, theta, so that is also equal. So obviously the other two angles will also be equal, and that is why these two triangles are similar, and so their corresponding sides are in the same ratio. In particular, PQ divided by OQ is equal to AT divided by OA. P cube is sin theta, O cube is cos theta, AT is tan theta. Well, tan theta means this is how tan theta comes. Okay, I should not say AT is tan theta. AT is just AT and divided by OA has length 1. So that is how AT is equal to tan theta. So with all these things, let us next see these inequalities about areas of some regions in this diagram. First, we have the area of this triangle OAP. It's not a right angle triangle, okay. OAP, the area of this triangle is less than the area of this circular sector OAP, a side of which is this circular arc. So it's like a piece of pie or a piece of pizza, like that. That is because this triangle is lying entirely within this circular sector, this piece of pizza, and there is some area that this triangle is missing. That is by strict inequality. The area of the pizza in turn is less than the area of this large right angle triangle OAT. Now, if you really calculate these areas, what is the area of OAP? 1/2 of base times height. Base has length 1 and height is sin theta. Area of the circular sector is 1/2 of radius square. Radius is 1 times that theta. Theta is being measured in radian, okay, keep that in mind. So this is the area of the circular sector. And then the area of this right angle triangle, 1/2 of base, which is 1 times height, which is tan theta. So that way, after cancelling this 1/2's throughout and doing the simplification, you get sin theta less than tan theta. Now what do we have from here? Let's see. Continue from here. So this was the last inequality. Next what we do, we divide throughout by sin theta and the inequality directions don't get changed. Is it justified? For that, sin theta has to be positive. Yes, sin theta is positive because we are in the first quadrant and theta actually is not equal to 0. So there is some height. So that is why sin theta is positive, and dividing the inequality by it is justified, and not just that, they do not get reversed because of this positivity. And if you do the simplification here, sin theta and sin theta get cancelled, you have 1 divided by cos theta. Now here you are looking at all positive quantities because these two are greater than 1 and 1 of course is positive. So now if you flip all of them, you take reciprocals of all of them, now the inequalities will get reversed. And you get 1 greater than, the reciprocal of 1 is 1 itself, and you take reciprocals here. So the inequalities previously were like this, now they will be like this. Now you look at these inequalities. The function sin theta divided by theta is trapped between these two functions 1 and cos theta, and you additionally know from properties of the function cos theta that the limit of cos theta as theta approaches 0 from the right side is equal to 1. Do you recall where this is coming from? This is coming from that observation which we have already made about the function cos theta, that it is continuous at 0. From that fact, this limit is coming. So as theta approaches 0 from the right side, this function approaches 1. And as theta approaches 0 from the right side, 1 itself also approaches 1, it's already at 1. So by the sandwich theorem, the trapped function also has to approach 1. So that's how we get the fact that the limit of sin theta divided by theta as theta tends to 0 from the right side, this right hand limit is equal to 1. Now next we have to somehow argue from this itself about the left hand limit. Let's see how. The next part of the argument is like this. We recall that the function sine theta is an odd function. We have already seen these things when we studied trigonometric functions. And theta of course is also odd. So the ratio of these two functions will be even. It's an even function. Because it's an even function, if you draw the graph of this function, it will be symmetric about the y-axis. So whatever happens on this side of the y-axis, on the positive side, an exact mirror reflection will happen on the negative side as well. What is happening on the positive side? As theta is approaching 0 from the positive side, the graph is approaching 1. So if theta approaches 0 from the negative side, from that side also the graph will approach 1. And that is why this symmetry tells us that the left hand limit of sine theta divided by theta at 0 will also be equal to 1. So that's how, without considering negative theta explicitly, that is drawing diagrams and doing all those things, still we have been able to make this conclusion. And that is why, because these two one-sided limits agree by theorem 5 from section 1.4, you can go back and see what that theorem is. It says that then the two-sided limit should also exist and be equal to that common value. So that's how we have this limit. Now let's use it to prove that other limit that I was talking about. Okay, so the next limit is this. We have to prove that the limit of cos h minus 1 divided by h is 0 as h tends to 0. And the more you work with these limits, you have to assume that whatever the variable is, that is being measured in radians if trigonometric functions are involved. Okay, that won't be said again and again. So here h is measured in radians. So what we do, we use this half angle formula from trigonometry to turn this cosine into sine. We know that cos h is 1 minus 2 sine square h divided by 2. And as such, in place of this numerator, you have minus 2 sine square h divided by 2. And you have h in the denominator, of course. Now you then next transfer this 2 here. Okay, in the denominator of the denominator, and you take the minus sign outside, and then you write this square of sine as this product, sine h divided by 2 times sine h divided by 2, and you club this h divided by 2 with this one sine. Now as h approaches 0, of course h divided by 2 also approaches 0. Now this limit will be the product of the limit of this and the limit of this. The first limit, by what we did just now by theorem 4, is 1. And what about the second limit? Sine h divided by 2 approaches 0 as h tends to 0 because the sine function is continuous at 0. That is how you get 0. Now with the help of these two limits, one involving sine and the other one involving cosine, we would next be able to differentiate the functions sine and cos. That we will see in the next calculus video. And tomorrow, of course, also we have our usual upload. I forgot, but I think tomorrow we have linear algebra, if I am correct. So we will see whatever it is tomorrow. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.